All right, thank you. So yeah, maybe I should try to clear up a little bit of the confusion first. As was stated, I'm Troy Johnson. Uh, I'm with Hewlett Packard Enterprise. Um, some of you may be aware that Hewlett Packard Enterprise acquired Cray last year. So HPE now has the Cray compiling environment. We're still calling it that as of this time. So the Cray branding there is persisting, at least for now. So I'm going to talk to you a little bit about our compiler environment, and this is kind of a high-level overview of it. I imagine many of you have not used the Cray compiler because it's really something that's only been available on Cray systems, and of course not everybody has access to a Cray system. So this will serve as a kind of a high-level introduction to what we have and what we do, and how we use LLVM. Let's see if I can advance my slide here. There. So first of all, what is it really? Well, it's actually a broader part of a larger product suite that we offer called the Cray Programming Environment, or CPE. So a lot of acronyms here ending in E, so I apologize. CCE, CPE, HPE. But it's part of the larger Cray programming environment, which is supported on HPE systems now. So both the legacy Cray systems and the HPE branded systems moving forward. This is composed of compilers, math and communication libraries, debuggers, and performance analysis tools. So we try to provide a complete set of programming environment applications for our customers to use. And again, these are only licensed for HPE systems. So we don't sell the programming environment separately for use on, say, your laptop. We sell it for the products the systems that we sell. Our compiler supports multiple languages, meaning Fortran, C, and C++. Those three are the ones that we support, and we support the most modern standards for those. We support multiple parallel programming models. So mainly that's OpenMP. That's what we see used the most for parallel programming. And we use OpenMP to target both CPUs and accelerators like GPUs. Well, I'll get to that more later. We also support two partition global address space, or PGAS, programming models, UPC, which is full name is Unified Parallel C, if you've heard of that before, and Cray, which is part of the Fortran standard. Both of those allow you to do, can be used for off-node communication. It's often viewed as an alternative to MPI versus OpenMP, which is more of a on-node programming model. And we support CPUs and GPUs from multiple chip vendors. So this is one programming environment suite, which is the same suite provided to our customers, no matter what particular CPU or GPU they have in their system. CCE's mission has a couple goals, really. Our main one is that we focus on HPC applications. I want to contrast that with open source, more broadly available compilers that really aim to compile anything. So if you look at upstream CLANG, or if you look at the GNU C and C++ compiler, those are compilers that really get used for a lot of things in a lot of different industries. Excuse me. And you know, they really have to deal with any sort of input per se, all sorts of applications, whereas our focus isn't really on that. Our focus is on high performance computing applications, which means that we can design optimization heuristics that are tuned for these HPC applications instead of the more general case. So we have a variety of cases where in our downstream compiler where we change defaults from what upstream LLVM uses because we've seen those defaults perform better for HPC applications. And, you know, frankly, even if we wanted to you know, change those defaults upstream, we probably wouldn't be able to, because it's just not something that works for everybody. It's not a good default that's more broadly applicable. It's very specific to the types of applications that we deal with. Our second goal is to give HPE customers a consistent compiler environment across products, which I think is a very important thing. Contrast that with each chip vendor's compiler, which supports only that vendor's chips. Right. So if you have a system with say Intel chips in it, and you get the Intel compiler, it only supports Intel chips. Or likewise with you know, AMD or other chip vendors. We've seen HPC customers switch chip vendors as necessary based on price performance, or more recently performance per watt. You know, based on how much it costs to power the system. And this allows customers to really choose across the product line that HPE and Cray offers, to select which one that they feel is most applicable to their workloads, without having to deal with the issue of, oh well, if I choose that particular platform, I'm going to have to use this set of software, and if I use that other platform, I have to use that other set of software. We kind of remove that from the equation by having a programming environment that works across the product line. The third thing is that it allows HPE to make more competitive bids for customer contracts. So particularly at the high end of the market, we see requests for products from customers that state that the system that we're trying to sell them needs to meet a certain performance metric for certain applications. And in order to meet those performance metrics in the request, you know, of course, one way of meeting that requirement is to simply throw more hardware at the problem. You can always try to sell the customer a larger system. Now, they might not buy it because it might be too expensive. So an often better approach is to try to meet that performance requirement by achieving it through software. So through compiler optimization, for example. So we do a lot of that internally, where we're asked, you know, can we make this application run faster to help provide a more competitive bid for a contract, and so that's an important part of what we do. And the fourth thing is that it allows HPE to respond quicker to customer bug reports and feature requests. So if you know, say HPE sells a system and we have a customer that runs into a problem, or they feel like a certain feature would be useful to them, they can come directly to us and ask for that bug to be fixed, or ask for that feature to be implemented. And so we don't have to then go and turn to a vendor compiler and ask them nicely to, you know, please support the feature, or please fix the bug. We can do that in-house. And, you know, with the open source compilers, that's important as well, because open source doesn't always move quickly. You know, those of you that have been involved in upstream LLVM know that, you know, sometimes suggestions for new features on the mailing list, or even getting bug fixes looked at can drag on for a long time. So, you know, we don't have to convince the open source community to adopt change that we want, or that a customer wants. We can just go do that directly ourselves. So I want to give you an overview of kind of how the compiler is architected at a high level. And this is going to go back to, I'm going to present this in stages because the architecture has really changed over time. And we recently made a change to using CLANG and LLVM. We didn't do that initially. So, you know, long time ago, before 2008, so before CCE version 7.0, we had an architecture that looked like this, where we had our proprietary Cray Fortran front end that we had developed in-house. We had an EDG-based C and C++ front end, which we had customized to some extent internally. And both of those would feed into a proprietary Cray optimizer. And the optimizer also had a code generator associated with it, which produced Cray vector code for the old Cray vector machines. And this Cray vector code we get linked with a variety of other libraries, some of which were you know, available on the system from the operating system, like glibc or the standard C++ library. Others were developed internally, like we have our own version of libn for highly performant math functions, or custom versions of memcopy and memset. We have our own OpenMP runtime. We have our own scientific libraries, like gloss routines. We have our own MPI and our own PGAS runtime. So, you know, depending on what the application was using, those libraries would get linked in, and thus you would have you know, your application produced for these older Cray systems. Moving on more recently, between 2008 and 2018, or between version 7 and 8.7, this changed a little bit in that we got rid of the proprietary Cray code generator, and we replaced it with LLVM. So in this model, we're using LLVM strictly as a code generator, meaning that we bypass most of what opt does because we've already optimized the code in our own optimizer. And LLVM lets us target a wider variety of processors than the old Cray vector targets. You know, most typically this is x86 code or ARM code. And then coming up to present day, since 2018 or since version 9.0, we've changed out the older C and C++ front end for CLANG. And on the CLANG side of things, or on the C and C++ side of things, we then use the LLVM optimizer to optimize instead of our older proprietary Cray optimizer. We've done quite a bit of work in the LLVM optimizer, as you can guess from this, to you know, port over things of interest to us from our older optimizer. But it's a more certainly more standard CLANG LLVM sort of pipeline on the C and C++ side. On the Fortran side of the house, we're still using our you know, all of our proprietary stuff. We're kind of, you know, monitoring progress of F18 and such, but we're not using any sort of open source Fortran. We're sticking with our own. And I guess the only other thing that changed here on this slide, on the right side, I've included compiler RT as part of the CLANG libraries, because we are you know, we are using compiler RT. We're using a couple other things from the LLVM project as well, like we use the LLD linker, for example. So why did that happen, right? So I showed you kind of the evolution of how the architecture changed over a number of years there. And so one obvious question that you might want to ask me is, well, why did you guys do that? Why did you change? Well, the use of LLVM really began when the end of when Cray custom processors ended. So at a certain point, roughly around 2007, as you saw on the slide, Cray stopped making custom Cray vector processors. And at the time, the direction that our product line was headed was we were going to start shipping Cray systems with x86 chips inside. And so in order to keep our compiler going and continue to have an in-house compiler, we were faced with a choice. We had to develop an x86 code generator from scratch in-house, which seemed a particularly daunting task, especially to do it on a short time schedule. Or we could, use an existing x86 code generator. So that's what we did. We got the LLVM cogen, and we modified our proprietary optimizer to generate LLVM IR as its final step, so that we could feed that into the LLVM cogen. And we now use LLVM as both an x86 and an ARM code generator in our current compiler. The next part is, well, why did we switch out the C and C++ front end? Couldn't we have kept that the same? Well, we really found that using CLANG was necessary to keep pace with C++ language additions. I would say C++ kind of been dormant for a while until C++ 11, and then it really took off. C++ 11 was a huge step, and that momentum's really continued in recent years with C++ 14 and 17, and they're really on a pretty solid 3-year schedule now for major standards releases. And we saw that CLANG was supporting these new standards very quickly, often before the actual standard was fully ratified. And we were finding it difficult to keep up with that. In addition, we saw that C++ was being used more frequently to write HPC applications. There's certainly a lot of older applications out there that are written in Fortran, and that even a few new ones that continue to be written in Fortran. But for the most part, what we're seeing, if someone has written an HPC application in recent years, it's they choose C++ or C for it, and we think in large part that's due to there not being a lot of newer Fortran programmers. Certainly, we see students leaving college that have not really ever seen Fortran, so that sort of tends to be an industry trend there. And when we mentioned this to customers, when we said, hey, what would you think about Cray having a CLANG-based compiler? It was pretty universal that everybody was excited by that, and so that kind of confirmed to us that this was a good way to go, and we're glad that we did that. So what benefits have we seen since we switched to CLANG and LLVM? Well, the first one, which is a really important one, is happier customers. They're really happy that we have support for the newer C++ language standards. They're happy that our compile time is faster. That's primarily a C++ issue. So C++ code, particularly very heavily templated C++ code, has the tendency to generate a large amount of code depending on how the compiler is implemented. And you also have to do a lot of inlining with C++ to get good performance. So depending on how your inliner works and how much code you inline, this really contributes to how many functions you have to compile and how large these functions are that you have to compile. And as we saw larger and larger C++ applications with more and more templates, the compile time of our older compiler infrastructure was just not dealing with that very well, versus CLANG and LLVM were able to cope with that much better. And better diagnostics. So CLANG's pretty well known for having good especially front-end diagnostics in terms of what, if there's any issues with the programmer's code. On the other hand, LLVM, the optimization part, is not as good at diagnosing optimization issues as our older compiler infrastructure is. So, and I've heard that mentioned in a couple talks during this workshop even. So that's definitely a place where we want to do some work at improving LLVM, how LLVM presents decisions that it made for optimizations, and reasons why it couldn't optimize certain things. Another benefit we've seen is that our developers, our compiler developers, spend less time maintaining analysis passes that every compiler has. So one of the downsides of having a fully proprietary compiler is that you have to do everything yourself. And that means even things that other compilers have, right? Every compiler has a dead code elimination pass. Every compiler, every C and C++ compiler on the planet has some sort of alias analysis pass. And if you're going to do everything yourself, you have to put effort into that. You have to maintain it. You have to keep it working across newer language standards, across newer applications that you haven't seen before from customers, and it takes a lot of work. And so by leveraging CLANG and LLVM more, we're able to spend time doing things that are more of real interest to us, such as adding more HPC value for differentiation in the market. Excuse me, and also analyzing performance of benchmarks and applications. So we really, didn't have as much time to do that before because we were spending a lot of time just maintaining the infrastructure and keeping things going. But now we have more time to really dig into user applications and benchmark codes and see where we can make new contributions. So how does CCE differentiate? Well, one way we do that is we add new optimization passes. So this is mostly done on in LLVM in the opt portion of it, although we do have a few cogent passes of our own. We add new features. So we have features in our compiler that the upstream doesn't have. For example, we have our own equivalent to the save optimization report that was mentioned in a previous talk. We have one that sort of tries to provide more information than what upstream does. We make modifications to existing optimizations and analyses. So we take a look at how the existing optimizations work, at the heuristics that are used to decide when to apply this optimization or when not to apply this optimization, for example. And we might tune the heuristics. We might change how some of the analysis work, add our own analyses. Adjusting tuning parameters is a big part, just kind of looking at the set of applications that we typically see and trying different values for different tuning parameters and selecting new defaults that work better for the universe of codes that we see our customers using. Last but certainly not least is integrating with the rest of the Cray programming environment. So we work closely with our performance tools group to develop a couple of products. So there's a Cray performance analysis tool that is it's essentially a profiler that gives customers more information as far as where their application is spending most of its time and how much of its time is spent doing computation versus communication, and where the computation time is being spent. And so our compiler is capable of adding more instrumentation to the executables to allow the performance analysis tool to collect more information. We also collaborate with that team very closely on a product called Reveal. And this was I was pleased to hear yesterday at one of the talks someone said, well, it would be great if there was a tool out there that would recommend to you how you should scope OpenMP variables. Well, we have that. It's called Reveal, and it's a graphical tool that works alongside the compiler. It kind of invokes the compiler under the covers to do the analysis, and it makes precisely those sorts of recommendations. It looks at what's being scoped as private or shared, and it says, well, you know, this looks like it could be private instead of shared, or you know, makes recommendations of that nature. And from within the tool itself, you can choose to accept the recommendation, and it will actually go and change the code for you. We also have modified the compiler to link with our own set of libraries. So we have a lot of you know, in-house work that's done on math library optimization, so that we have you know, good implementations of common math functions that we see called by customer codes. Let's see. I want to talk a little bit about our open source strategy. So how does CCE work with upstream CLANG and LLVM? We like to submit things upstream when we can. We want to be a good, you know, open source citizen in that regard. But most of what we submit are bug fixes and infrastructure improvements. So if we, you know, for example, if we find a case where maybe the upstream compiler is doing something illegal, like it's you know, vectorizing a loop that isn't vectorizable or something like that, we would report that as a bug, and if we're able to, submit a bug fix for that. For infrastructure improvements, that's kind of admittedly, that's kind of a self-preservation strategy, because if there's a broader infrastructure change that we want to make, it's harder to maintain that downstream. So if we see something that would be difficult to maintain of that nature, then we try to you know, work with upstream and get that discussed on the mailing list, and try to get that integrated, so that it's not as big of a merge conflict headache with us in the future. We maintain a number of things as downstream changes, primarily performance improvements. We don't contribute back any performance improvements to upstream. We maintain that as a you know, advantage to differentiate our compiler in the market. Likewise, we don't submit any of our differentiating features. But and other things that we keep downstream is anything offered upstream which the community did not want or could not agree on. So we have at times you know, floated proposals that have said, you know, we'd really like to do this, or you know, here we've got code that does this, you know, do you guys want it? And sometimes we've been told no, that you know, that's not of interest, or you know, it spawned some discussion, but there wasn't any consensus on how to actually integrate it upstream. So we continue to maintain stuff like that downstream. Likewise, we maintain downstream anything that was removed by upstream that we wanted to keep. So occasionally stuff disappears on us, and we didn't want it to disappear, but someone thought it would be a great idea to take it out, and so we will revert those patches locally and put it back. We try to closely track upstream developments. We integrate upstream changes about monthly into our Git branch, and we release major new CCE versions about 2 months after upstream releases a major CLANG version. So that's been kind of a recent schedule shift for us to try to track upstream releases more closely, so that we pick up the last of the bug fixes that went into the release branch upstream, and we have a couple months after that to run through all of our in-house testing and make sure that that everything's working as we expect it to. We keep very close track of our downstream changes. We use new files whenever possible, and whenever we don't, we add comments. So it's very easy for us to go through our downstream code base and find out where we've added things, where we've changed things. And we try to guard our downstream changes with options. So one of the challenges with having a downstream LLVM compiler that we've experienced, and that I don't think upstream LLVM really has that nice of support for, is when you change it, even a trivial change can really cause almost all of the upstream tests to fail. And we'd like to continue running all of the upstream tests to make sure that that they're all still passing. So we have to have a way of kind of taking our compiler and running it with our changes turned off. And that's been useful for making sure that all of the upstream tests still pass. And then we have our own tests for things that we've changed. So we kind of make the argument that, well, if all of the upstream tests continue to pass without our changes, and our new tests pass with our changes, then everything should be working correctly. We also, of course, still compile full applications as a testing step to make sure that that all works well. And so that gives us confidence that even though we've made significant changes to the upstream compiler, that it's still a solid performing compiler. We're active upstream on a couple of things. We monitor the email lists. I wouldn't say closely because it's a lot of traffic, but we sort of make a community in-house community effort to each person tries to check it every now and then, and we hope that we have enough enough coverage there to stay active on the lists. We've attended the past two US LLVM developer conferences. We don't really get a chance to make it to the international ones, but hey, if everything stays stays virtual like this, you might see us at more in the future. We're involved with a number of upstream projects. We're active helping ARM upstream with SVE. We're active helping with the floating point trap support in LLVM, because until recently that wasn't really given much of a thought in LLVM. LLVM tended to just ignore that traps existed, but for a certain class of customers that we have, floating point traps are very important. Our OpenMP team has been actively helping with getting OpenMP 5.0 working. And there's other projects where we're kind of not as intimately involved with them, but we're sort of monitoring their progress. One thing that we've been watching is aliasing improvements for C restrict. So the issue there is that upstream CLANG and LLVM don't really recognize the restrict keyword for local pointers. They recognize it for function parameters, but not for within the body of a function. And we've really wanted to see improvements on that for a long time now. We actually went with the solution in our downstream compiler that was pretty quick to do, that works for, I would say, probably 99% of the cases that we see that our customers use. But we knew that patch would never get accepted upstream because of that, final 1% that it wouldn't work for. So that's one advantage of having a downstream compiler, is we were able to make that change without having to get the community to agree on it. And we've certainly seen benefit from it. If upstream does make those improvements, we'll certainly switch to that. But in the meantime, we have our own sort of only slightly dangerous change. As I said, 99% of the tests that we've thrown at it pass, and so we just made that change with an option to turn it off. And for the most part, that's been working fairly well. We've been keeping our eye on FLANG since we have a Fortran compiler and we already use LLVM. It's a sort of a obvious thing for us to watch and see how that's going. But it's not really at a stage yet where we can use it and try it. So that's just kind of a monitoring effort there. And yeah, that's the end of my talk.